Hello again. So recently I saw a video. Guy was talking about a place where they supposedly found radioactive skeletons. Now the guy later said this has been debunked, um, and I sort of looked some stuff up, and I'm not going to go into that. I do believe it has been debunked properly. I might do that in another video. I just got to wondering, what would it take to make a radioactive skeleton? So that's what I'm going to be talking about here. So I looked up some information on the site itself. Tried to find information about these supposedly radioactive skeletons and could find very little. The sites which are pushing this idea and that the ancient people had nuclear bombs and irradiated their skeletons, they didn't give the details I was looking for. I was looking for stuff like dose rates coming from the skeletons, what isotopes are in these skeletons, which we have the equipment, we can identify isotopes fairly easily. So this is all stuff I was hoping to find. None of the articles which were pushing the idea of radioactive skeletons had it. I was going to go into more detail on these articles, but I figured things would get very long, so I decided not to. Might do that in a future video, just sort of point out what's going on with it. So, some basic facts. The place is called Mohenjo-Daro. It's in the Indus Valley, the Larkana district of Sindh, Pakistan. It was discovered by Europeans in around 1922. Basically, a Buddhist monk took a European explorer and said, "Hey, I know where these ruins are." So the people of the area knew they existed. Europeans didn't know about them until 1922 and didn't start studying it until then. It's believed to have been built around 2500 BC and had a population of about 40,000, and then it died off around 1700 BC. And the big mystery about all this is it just seemed to, it just stopped. People didn't necessarily just disappear, but it's just like this civilization or community just ceased to exist. And so there is a big mystery what happened to them. They excavated down to street level and found 44 skeletons sort of around, and these are the ones which were supposedly radioactive. And so, and people studying these skeletons are claiming that yes, these were radioactive skeletons, even though there's very little evidence to suggest that, in my opinion. Like I said, couldn't find any information about what isotopes were supposedly coming from these skeletons or how much energy or anything like that, dose rates, stuff that I could use to actually analyze this and say yes or no, I believe this. So instead, I've gone to what would it take to make a radioactive skeleton. Now, suppose this is radioactive. It's sitting there. Alpha emitter. Alpha jumps out, it hits me. It may or may not do damage to me, may or may not give me cancer. It's not going to make me radioactive. I go walking down the street, someone's not going to hold up a meter to me and it's not going to go off. Beta emitter, same thing. I can be exposed to it. I'm not going to turn radioactive from being exposed to it. Gamma emitters, same thing. Neutrons. Now, if a neutron jumps off this and hits me, it's possible it could get absorbed into one of my atoms, and that atom could become a new isotope. So I could change from being a non-radioactive atom to a radioactive atom. So, neutron exposure might turn me radioactive. Like that, it's just sitting there right now, though. I pick it up, I open it up, I get radioactive material on me. Now that can be absorbed into my body. potentially, depending on what chemical it is. Even if, or if I have an open cut, it can get in there, it can get into my body. If I lick my fingers, it can get into my body. So now I can become radioactive because I'm ingesting the material. That's one way I can become radioactive. Um, Now all of this different chemicals or different elements have different target organs. So it sort of depends on how your body uses the material. Carbon and hydrogen, your body sort of uses for everything. So the target organ is your whole body, quote unquote. And there's a biological half-life. Just as the stuff is decaying normally, your body's using it at a certain rate. And so there is what is considered the biological half-life. So depending on, like I said, carbon and hydrogen, your body uses a lot of. So it's constantly, I absorb some of it. My body uses it to build new cells, do whatever. Those cells eventually die and my body eliminates it. So there is, the biological half-life. If I ingest so much radioactive material, how much will my body dispose of through normal biological procedures in a given amount of time, basically. Like I said, that's tritium, or that's hydrogen and C14, which your body uses a lot of. Other things like iodine, most of that goes to your thyroid. Well, actually, most of it goes to your blood, but a significant amount goes to your thyroid, which is considerably smaller than your blood system, your cardiovascular system, that it looks like it's going to your thyroid. So that's considered the target organ for iodine. Yeah, it depends on how your body uses iodine to make hormones and stuff, and a lot of that's done in the thyroid. So the thyroid is the target organ for iodine in most cases. And there are different elements have different target organs depending on what your body uses that particular material for. So we are looking for things which have a target of bone or bone marrow. So before we get there, let's look at the human body itself. The body is about 99% of the body is composed of 6 elements. So, and when I say these percentages, they're being given by mass and not by number of atoms. You got to understand that. For instance, oxygen makes up most of your body, according to most places. 18.5, no, wrong number. 65% of your body is oxygen, according to most websites. And that's because your body is also 60% water, 60 to 65, depending on who you're talking to. And water is H2O. Like I said, we're doing by mass instead of by number of atoms. So our oxygen is atomic mass of 16, hydrogen atomic mass of 1. So a water molecule is atomic mass of 18, 16 of that is oxygen. So yes, you have twice as much hydrogen in your body, actually more than twice as much because hydrogen is used for things other than water. But you have more than twice as much hydrogen in your body than you do oxygen, but oxygen still makes up a greater percent just because the atoms are bigger. Carbon, 18.5%, hydrogen, 9.5%, nitrogen, 3.5%, 2.5% is split between calcium and phosphorus. I couldn't find the percentages for those. Then, let's see, there was another 1.5% is split between 5 elements, and those are potassium, sulfur, sodium, chlorine, and manganese, or not manganese, magnesium. And then 0.15% of your body is made up of other elements. And couldn't find any details deeper than that. This is an average, of course. It's not everyone's the same, but it's sort of an average reference. So let's look at these. Now, most of these, so we're looking radioactive skeletons. We want things which are in bone. So we looked up what about bone composition? What did I find here? Let me see. Our bones and teeth contain isotope. Let me move a window here. Our bones and teeth contain stable isotopes of oxygen, strontium, nitrogen, and carbon. So that's useful information. There was another thing here. Bone is a composite material consisting of both inorganic and organic components. The inorganic component is primarily crystalline hydroxyapatite or something like that. And it gives a chemical formula for it. I actually found two different chemical formulas on different websites. And the organic component of bone comprises more than 30 proteins, and type 1 collagen being the most abundant, and it doesn't give any detail about the chemical makeup of it. I will point out that basically this crystalline hydroxyapatite, or however it's pronounced, sorry about that, it's largely calcium and phosphorus, which I did find there was a reference that a large amount of the bones, about 38% of bone is calcium and about 17% is phosphorus. So over 50% of your bones are calcium and phosphorus. So those are things we're going to be looking at. Okay, so I ingest material. It goes to different parts of my body and potentially makes them radioactive. Now, so did the ancients have nuclear weapons? Nuclear fallout. Look this up. Where was that? Okay, about 96.9 is composed of 10 elements of nuclear fallout. And this is what would be detectable after a couple of days. There's some shorter-lived isotopes which just go away quickly. So we got two isotopes of strontium 89 to 90, yttrium 91, zirconium 95, ruthenium 103 and 106, cesium 137, cerium 141 and 144, and promethium 147. Looked up the target organs for these just to see what's going on with them. So strontium will go to the bones. That's good. Yttrium, primarily the eyes, the liver, and the lungs. Zirconium, I couldn't find any information on its target organ, but it's only got a 66-day half-life, so the skeletons, which are thousands of years old, if they had zirconium in them, it would have decayed away long before we got to modern times. Ruthenium 103 and ruthenium 106, the heart is the primary target organ. Cesium 137, liver, intestine, heart, and kidneys. Cerium, liver and spleen. Promethium, unknown, but possibly bone tissue, they say. So, nuclear fallout, promethium is the one which is going to affect your bones most likely. Now, the problem is the bomb going off isn't going to just immediately send these elements into your body. You have to ingest them somehow. So most likely, water supply gets contaminated, you drink water, you get radioactive material in you. Soil is going to be contaminated, food that grows in it is going to be contaminated, but it's going to be a longer process growing the food and eating it. So contaminated water is your most likely bet. But it can get, there are other ways it can get into you. You can breathe some of it, stuff like that. Now, our best, for a nuclear explosion, our best studies would probably be Hiroshima and Nagasaki. We were looking primarily at cancer rates from that and not at like radioactive bones or anything like that. So not a lot of information from that. Chernobyl, we did start getting like strontium in the wildlife and stuff like that. We did start doing studies on that. A nuclear reactor meltdown would produce many of the same isotopes found in fallout, but they would be producing them at much smaller amounts. So, yes, we can get some information from those studies, but it would be sort of a bad analogy to try and figure out, because we haven't found caribou with radioactive skeletons. So, On that side, we could say, no, this wouldn't be happening. On the other side, we could say, but wait a second, we're using much smaller amounts of radiation, so maybe the caribou would get more. Okay, so back to the human body, though. I started looking, so neutron absorption. I've studied some of this in school. And this we could go to, what if someone used a neutron bomb? It's designed minimal structural damage, but massive radiation damage. And it would be releasing neutrons, the body could absorb it, and so could that turn a skeleton radioactive? So looking at the body, so the rate of absorption, or they have what they call the cross-section for different isotopes. And the cross-section is primarily, it's sort of a bad analogy. It's more the probability of a neutron being absorbed by this atom. And it's not based on the actual size of the nucleus, it is based on the buildup of it. How many protons, how many neutrons, how welcoming is it to a new neutron being absorbed, let's say. Again, that's probably another bad analogy, but it's sort of the best I can do at the moment. For reference, because it doesn't give it in percentages, it doesn't say there's a 30% chance that this neutron would be absorbed. It measures it in things called barns. Basically, someone got the idea hitting the broadside of a barn, so they named the unit of isotopic cross-section the barn. For reference, boron is used to absorb neutrons at control rods for reactors. It readily absorbs neutrons, and it's got 3,840 barns as its basic average, I guess, calculated. That by itself doesn't tell us much, again, because what is a barn? How does this reflect other isotopes? It doesn't really give us it's a probability of absorption, but it doesn't really give us a percent absorption or something that we can compare to our day-to-day lives of probability. But just for reference, 3,840 is considered useful for stopping a nuclear reactor. So that's absorbing a lot of radiation from a source which is specifically meant to put neutron radiation into an area. So looking at our elements, so oxygen. We have a lot of oxygen in our body. It doesn't, it might occur in bones. I couldn't find a measure of that. So naturally occurring oxygen, 99.75% is oxygen 17, which is stable. 0.205% is oxygen 18, which is also stable. Their cross-section is in tenths of millibarn, so very small compared to that of boron. The longest half-life of anything radioactive, so oxygen does manage to absorb a neutron and becomes radioactive. The longest half-life of any radioactive oxygen I could find was 27 seconds. So neutron bomb goes off, I become radioactive with radioactive oxygen. It's going to be undetectable in about a day at the most, unless I get really, really irradiated. Carbon, let's see, carbon 12, 98.93% of naturally occurring. Carbon 13 is 1.07% of naturally occurring. Both are stable. Carbon 14 has a 5,715 year half-life, so I irradiate someone's carbon 13, it turns into carbon 14. Carbon 13 has 1.5 millibars, carbon 12 has 3.5 millibars, so still fairly low chance of absorbing a neutron. But if it does, it can turn into something with a 5,000 year half-life. That might be detectable later on. Carbon 15 has the next longest half-life, and it's 2.5 seconds. So we are really relying on carbon 14. How much carbon is in bones? We don't know. Again, there is organic material in bones, so some of that's probably carbon. Hydrogen is the next highest isotope, or next highest element. Hydrogen 1, 99.9885% of all hydrogen is natural. Deuterium, 1.07%. Both are stable, or some people think deuterium might be radioactive. It just has an extremely long half-life, so it's hard to tell. Not going to go down that rabbit hole here. Tritium would be the next highest, or next isotope, which so deuterium 1.5 millibar. Well, no, that's wrong line. 0.5 millibars. So deuterium unlikely to absorb a neutron, but if it does, it will turn into tritium. Tritium has a half-life of 12.3 years. Longer than most we've been talking about, but at the same time, over the course of the thousands of years that these the city's been sitting undiscovered, most of that would have decayed away to background. It's also very hard to detect. So saying radioactive skeletons with tritium, because it's very low energy, it's like you would have to actually cut the bones up and run them through an analyzer as opposed to waving a handheld detection device at them. So very hard to detect. So when they're saying radioactive skeletons, I don't think they're talking about tritium. Nitrogen, 99.632% is nitrogen 14. 0.368% is nitrogen 15. Both of those are stable. Nitrogen 14 has 1 millibarn cross-section. Nitrogen 15 has 0.02 millibarn cross-section. And 7 seconds is the longest half-life of any radioactive nitrogen I could find. So, again, bombard nitrogen with neutrons. If it does become radioactive, it's the radiation is going to decay away within a day, basically. So you're not going to be able to detect much of it 1,000 years later. Okay, calcium. So calcium, there is some naturally occurring radioactive calcium, but not a lot of it. So calcium 40, 96.941%, and that's non-radioactive. 0.41 barn. So it is more likely to become radioactive, or more likely to absorb a neutron than some of the stuff we've been talking about, but still very low. Calcium 41 is naturally occurring radioactive material with 100,000 year half-life. Actually, no, that's not naturally occurring. My mistake. Sorry about that. So carbon 40 absorbs a neutron. It might turn into carbon 41. And if it does, then yes, this could potentially survive long enough to be detected by modern day men. And it is calcium. It goes to the bone. So that would make some sense. Or it's in the bone naturally. Calcium 42, naturally occurring, also stable, 0.64%, 0.7 barns. Calcium 43, again stable, so 0.135%, 6 barns. Calcium 44, 2.086%, it's also naturally stable, 0.84 barns. So again, we got this chain of naturally occurring carbon, which is stable, and if it absorbs a neutron, then the product is also going to be stable. So calcium 45, naturally occurring, well, no, actually not naturally occurring also, but 163-day half-life, so we got something significant going on there. But again, over the course of 10 years, that's going to be decayed down to about background levels again. Over the course of 1,000 years, definitely we wouldn't detect it in our skeletons. Calcium 46, 0.004% of the naturally occurring calcium, and it is stable, 0.8 barns. That would, if it does absorb material, it will go up to calcium 47, which is not naturally occurring. It's got a 4.5-day half-life, so that's going to go away quickly. Calcium 48, 0.187%, and this one is naturally radioactive with 5 times 10 to the 19 year half-life. So this is something you might have this in your body naturally, whether you're exposed to neutrons or not. It is radioactive, but it makes such a small percent of our body that we wouldn't detect it. And then all the other isotopes of carbon, or not carbon, calcium I could find. Again, the others are not naturally occurring, and they all have short lives of minutes or less. So, again, someone thousands of years ago exposed to neutron bombs and gets these higher elements of calcium, we wouldn't be able to detect them today. Okay, phosphorus, also an interesting one. So, phosphorus 31 makes up 100% of the naturally occurring phosphorus that we know about. Approximately 100%, let's say. Just to play devil's advocate. It is stable. It's got a cross section of 0.17 millibarns, so very unlikely to absorb a neutron. If it does absorb a neutron, it turns into phosphorus 32, which has a 14.3 day half-life, so very unlikely to be detectable after thousands of years. If that were to absorb a neutron, it would turn into phosphorus 33 with a 25.3 day half-life. Again, highly unlikely to be detectable after thousands of years. All higher forms of phosphorus have half-lives of less than a minute. So I'm not going into the barns on these radioactive elements because most sources don't give them, because it's sort of hard to measure how well something can absorb a neutron when that item itself is decaying. So most sources, unless it has a very long half-life, don't try to give you the cross-section of a radioactive element. Okay, potassium, sulfur, sodium, chlorine, and magnesium make up about 0.85% of the human body. I could go through. Potassium has some naturally occurring radioactive material. Basically, there I've heard stories of people working in a plant where they got like the detectors at the door, want to make sure people aren't taking radiation out with them, or contaminating themselves. They'll eat a banana for breakfast and they'll set off the machine going into it because potassium 40 exists in bananas and it's radioactive. It's naturally occurring radioactive. Then at the end of the day they'll leave and it's gone because they've gone to the bathroom and eliminated most of the potassium from their bodies. So potassium doesn't go to the bone as much as you would think because it's goes out. I think mostly goes to the kidneys because it's expelled in urine mostly, if I'm not mistaken. Sulfur, very short half-lives and everything. Sodium has 2.6 years. Sorry about that. Read that wrong. Is the highest half-life for sodium. Chlorine, naturally occurring chlorine, 75.78% of what is naturally occurring, has a half-life of 30,000 years, and that's chlorine 35. 43.6 barns, so it is actually more likely to absorb a neutron than most of what we've been talking about, and it'll turn into something non-radioactive if it does that, or something with a much shorter half-life if it does that. Let's see, chlorine 37 makes up the rest of the naturally occurring chlorine, and it is stable. Most other isotopes of chlorine have half-lives of minutes or less. Magnesium, again, we're going into 78.99% is magnesium 24, short half-life. 10% is magnesium 25. Actually, stable. Both of those are stable, not short half-life. My mistake. Low barns is what I meant. 0.05 barns for the first one, 0.2 barns for the second one. 11.01% is magnesium 26, got 0.04 barns again. All isotopes also stable. All the artificially made magnesium, which is radioactive, has half-lives of hours or less. That's most of what naturally occurs in our body. So we're radiated by a neutron bomb, it's unlikely to make our skeletons radioactive again. Or if it does, the radiation's going to decay away before thousands of years pass and someone discovers the city. Okay, other things you can absorb, and this would be stuff that can potentially come from fallout. That's not likely. Radium. I've talked about the radium girls in a past video. Yes, radium your body will absorb. It's got a long half-life. Radium 226 has a half-life of 1,599 years. So, yes, if I absorb this, my skeleton will be radioactive long enough for someone to detect it in 1,000 years. Thing about this is, again, it's not in your body naturally. So neutron activation from a neutron bomb is not going to do it. Another kind of nuclear device contaminating the water supply can do that. Strontium also goes to the bones. This is also produced in, as we discussed earlier, this is also produced in from radioactive or from nuclear devices. But its longest, strontium-90 has a 29-year half-life, so it would be down significantly. Polonium also goes to the bones, and fairly short half-lives on these. Actually, 102 years is the longest half-life I could find for it, but that's in a isotope which is very infrequent. So yes, there are some isotopes which could be produced by a nuclear device which would cause our bones to become radioactive. Thing about that though is the idea that part of the thing people are pushing is these skeletons are found out in the street. It's like they died suddenly, which wouldn't happen. Nuclear bomb, well, with a neutron bomb, it could happen. Only it wouldn't happen with these particular elements. It would happen with other elements which would decay away fast, so we wouldn't be able to detect it. Our standard uranium or plutonium bomb, it could happen, but the bodies wouldn't be found out in the street. Like they wouldn't just like drop dead suddenly in the street. This would be, again, the fallout gets in the water supply. I drink the water. I get cancer. I get sick. I die at home in bed. So no real, again, claims of radioactive skeletons found in this city. No real proof of it. And looking at what it would take to make a skeleton radioactive, it's highly unlikely that any of this would have been made with a nuclear bomb as we know them. If the ancients discovered a new kind of bomb, then maybe, yeah, this could happen. But other than that, highly unlikely. That's it. I've run longer than I normally do, but I enjoyed it. Have fun. And have a good day. Don't drink the radioactive water. And this is not turned off. Come on.